Hello everyone. Welcome to today's webinar on finite element analysis using MIDAS FEA. My name is Abhishek and I'll be taking you through today's presentation. If you can hear me and see my screen, just type yes on the questions window and we can then proceed with the presentation. Okay, so today I'll be covering basically a few basics of modeling in the software. We'll take different examples from steel structural analysis to reinforced concrete analysis. We look at nonlinear analysis, construction stage by stage construction, and linear buckling analysis, and we'll go through a few of the post-processing features of finite element analysis package. So before going to the examples, I'll just give you a brief introduction to the graphical user interface of the software. So as you see on the screen, you can see the MIDAS FEA window with all the menus on the top. This is a geometry-based software. So to create the finite element mesh or to create the structural model, we start with the geometry first, which involves simple geometry shapes such as curves, surfaces, solids, and few geometry transformation features such as translation, rotation, scaling, and also after modeling the geometry, we mesh the model geometry to create the finite elements. So now finite elements supported in FEA package is is a list of line beam truss elements. We have plate elements. Again, plate elements can be triangular, quadrilateral, and also higher order plate elements, which are called quadratic elements. So basically 3-noded, 4-noded, as well as 6 and 8-noded. Same thing goes for solids. You have lower order solids, volumes, and higher order solids. And then analysis tools. Analysis tools include definition of materials, properties. Okay, so section shapes, plate thicknesses, and then things like boundary conditions, loads. Variety of loads can be defined, forces, pressure loads, and also arbitrary loadings, which do not depend on the mesh. And then we have the post-processing tools. So these are used to extract results in both graphical as well as table format. So we'll be looking into all these options in detail. At the center you have the main modeling space. You can visualize the model being built here and also look at the results graphically. On the right hand side you have some display tools such as different view modes, front view, top view, etc. And then at the bottom you have a message window. So message window will basically show you any errors or warnings that you do in while modeling, and will also report you the different steps during the analysis. So you can always see if your analysis is going well or not from the message window. And right at the bottom of the screen you have the units panel. So this takes care of the unit system. Any type of units you can set here and start modeling in the defined units. On the left hand side is a tree menu. We call it the works tree. Now there are two parts of this works tree. One is the pre and the post. Pre-works tree is for modeling purposes only. So you can look at the geometry, shapes and mesh that you have defined, properties. Okay, so everything related to modeling, you can extract all the information from the works tree. Okay. Also, you can edit things by simply right-clicking and using the edit function. You can modify the properties or loads or boundaries, anything. And post works is for results. So this will list out all the different results for during analysis, like reactions, displacements, forces, stresses, strains, etc. So all these results can be looked at from the post works tree. And then there is a properties window, which basically gives you a summary of the properties associated with an element or a mesh. Also allows you to manipulate the results, how the results are going to be displayed. You can control from the properties. Okay, so now what I'll do is just create a new model. Okay, so first example, what I'll show you is the different ways of modeling. Okay, so first example will focus mostly on modeling. So I'll click on new project. Okay, so that's how you start a new project, file, new project, and then a window comes up. You can set up the analysis type, 3D or 2D. So let's say 3D. Okay. Now in MIDAS FEA you have two types of unit system. One is the global coordinate system, which you can see on the right bottom corner here, XYZ, and the other is the work plane, which is used for modeling in a 2D plane. Okay, so the grid system that you're seeing is indicates the work plane. Okay, if you want to draw anything in 2D, then it's easier to plot directly on the grid and model things in a 2D plane, also called the work plane. Okay, so back to the pre-works menu. Okay, so from the pre-works menu we can set what is going to be our work plane. So let's say if it's a building that you're modeling here, then if you're modeling the plan in XY, global XY, and elevation is in the Z direction, then if you're modeling the plan, then you should set the work plane in XY. Okay, if you're modeling the elevation, you should set it in XZ, so it becomes like this. And then switch to the work plane, which can be accessed from the option on the right hand side, which says normal. This is a normal view of the work plane. So then you can start plotting things directly on the grid and start modeling your geometry on a work plane. So let's see how to model things on a work plane. We have got geometry option, work plane. Okay, you can set the grids. Okay, so the unit system currently is 1 meter by 1 meter. So if I say 0.1 is the grid spacing. Okay, and I put number of grid points I want. So let's say 100. Okay, and there is a preview button before you click apply on any feature. There is a preview button in the dialog box. If you click there, it will show you the preview of what you're going to apply. Okay, so you can always correct if you're doing anything wrong, and then again click preview, and if it's fine, then you click apply. Okay, so I'll just click OK. So I've got a finer grid now. Okay, alright, so if you remember, my grid system is XZ. Okay, so it's XZ, and the grid setting is 0.1 meters, 100 times. Okay, now we'll start modeling. So to model anything in 2D, we use the option curve, create on work plane. And there are different options. If you have used AutoCAD, you will find the similar tools here. Okay, so if I want to draw a rectangle, use the rectangle option here. So let's say a 2D beam I want to draw. Okay, so rectangle option, and there are a few snap tools available on the top. So I'm going to use grid snap, which will allow me to snap on the grid points. Okay, so let's say the height or depth of the beam is 0.5 meters. So I just draw a line from here and say the length is 2 meters or 2.5 meters. It's up to here. Okay. Now there are a few navigation tools. There's a pan tool here. You can also click Control and middle mouse button to move the objects. Okay, and if you use the middle mouse button only, then you can rotate, and if you scroll in and scroll out, you can zoom in and zoom out. Okay. Okay, now you see there's a wireframe here. If I remove the grid from display, it will be more clear now. So I've got a rectangle here. Okay. Now the same thing, same geometry, I can also model it as a face, like a surface. Okay, so this is just a wireframe, just lines. Instead of modeling lines, I can use the make face option, and I can draw again the same rectangle, but this time as a face. So this is a 2D face now. Okay, this is one surface, and this is a wireframe. Okay. Okay, now why I did this 2 times is because I want to show you the different ways of meshing. Because when you get the geometry, modeling geometry is fine, but for analysis it's the mesh that is important. So there are different ways of generating mesh in the software. Okay, so you can use the same. If you want to generate a 2D beam, okay, you can use simple lines to generate the beam. You can also use a surface to generate the mesh for the beam. Okay, so basically a 2D beam will involve 2D plate elements. Okay, so before defining your plate elements, you have to have some materials. So the materials can be defined in analysis material, create, right? So you have different types of material you can select, isotropic or orthotropic. Okay, so I'll just go for isotropic. Again, from the you can enter elastic modulus and all these properties manually, or you can select from the database, say ENRC Eurocode. Select C40 for example. C40, and I'll stick to elastic for now. Okay, we'll see other options later on. Okay, and yeah, and then click OK. So that's one material defined. I'll close this, and the next thing is defining a thickness for the plate. Okay, so we go to properties for analysis property for that, 2D, and define a plate thickness. So let's say if it's 300 millimeters the width in the out of plane direction, then 0.3. Okay, and rest of the things we'll just keep it. We want uniform thickness, so I'm just keeping it as 0.3. You can have varying thickness here. I won't go into that detail of varying thickness. So just keep it uniform for now. Okay, so now what we do is we've got mesh options. Okay, so I'll quickly go through a few of the mesh options. Okay, starting with auto mesh, which is a quick feature where you select the geometry. Okay, if it's a face, we select a surface and or a face, and and that face gets converted into a series of plate elements. So if I select face and select this face, okay, give a size, okay, 1 meter, or if I click on this arrow, it will suggest some other size for me. Okay, so 0.3 meters, and you see those dots here. These are the location of the nodes. Okay, when you mesh it, it will be divided into nodes and elements, so you can see how fine your mesh is going to be. Alright, so when you click apply, you will get a series of plate elements. So it's divided into several plate elements now. Okay, if I undo it, you can undo unlimited times, so you can go back to an n number of steps. So if I undo it, reduce the mesh size, okay, and then apply, you get another type of arrangement of nodes and elements. Okay, now there are different types of meshing tools available. You can either select quadrilateral, triangular, and there are different meshing algorithms there. Okay, so if you want a mixture of quadrilateral and triangular, then Delaunay mesher. But again, it depends on the geometry. For example, if you have a curved surface, okay, a surface which is curved in horizontal in a plan view, and you want to mesh it, then it's difficult to use quadrilateral. So using auto mesh, so you may end up with some triangular elements. So quadrilateral plus triangular can be used. So if I select triangular and click OK, apply, so I get this type of arrangement. Okay, now for accuracy of the analysis, the more number of nodes you have in an element, the more accurate will be the analysis. So that means that quadrilateral elements will in general give better results than triangular elements. Okay, also the aspect ratio of the mesh of the element is important. Okay, it should not be very skewed, it should not be very the ratio of the height versus the width should be at least within 1:2 or 1:3, and not beyond that. Then things like if you want to do a very advanced analysis such as nonlinear analysis, or if you add reinforcement in your beams and you want to look at reinforcement stresses, or if it's tendons, pre-stress tendons, you want to look at the tendon losses and all those things. So for such type of analysis, the higher order elements are preferred. So there is an option which says generate mid-side nodes. This will basically generate the higher order element. Mid-side nodes means, say if it's normally a triangular element is 3-noded. Mid-side node means it will create internally it will create nodes at all the midpoints of the edges. Okay, so there will be 6 nodes instead of 3 nodes, and you will get more points, result points, stress result points. So the analysis will be more accurate, and you will get better results. But more number of nodes also means analysis time will increase. So depending on the extent of the analysis, you need to check which type of setting suits your model. Okay, most simple geometries can be analyzed using lower order elements. Okay, so that's one way of meshing. If you have a face, you can use the auto mesh function. Okay, then there's an option called map mesh. Okay, map mesh is basically, it forces the geometry or the area where you want to mesh. It forces it into a more uniform and regular mesh, quadrilateral mesh. So when you use map mesh function, you generally end up with a very regular mesh. Okay, so if I mesh this, if I remove the grid and say 0.1 meters, okay, preview. So you see it always cuts the geometry into regular shapes, regular quadrilateral. Okay, you can try it on curved geometry as well. Map mesh will give you a regular type of mesh. Okay, let's try a curved face now. So what I'll do is create on work plane, use the circle function and just draw quick. Oops, escape. Okay, and make face, so it will be converted into a surface. Okay, so I use auto mesh. Oops, I'll just reduce the mesh size. One. So you get this type of mesh. Okay, so it comes up with whenever you have a curved surface and you want to map mesh. Okay, it comes up with if the surface is regular, okay, it does not have many curved portions, then it's easy to generate a regular mesh. Okay, so map mesh can be used directly. Okay, but if it's a curved geometry, then you will get this type of a message which will tell you that it's failed to generate 2D map mesh. Okay, because it couldn't find um, the number of the required number of sites for generating the map mesh, because it's a completely curved geometry. So for creating the mesh, the map mesh for such situations, it's good to first create the node points, okay, where the nodes are supposed to be. So let's say if I draw okay, if I look at this particular example, this wire, okay, if I want to mesh this wire into plate elements, okay, so I go to mesh size control. Okay, this option is used when you have any type of geometry, curved or regular geometry, and you want to still create a regular type of mesh. Then we use this option, size control. Okay, and this also allows us to have a more efficient mesh, because you may not want the same mesh size everywhere. So if you are doing a very detailed analysis, you may want to have a finer mesh near the supports, or finer mesh near where the loads are applied, but a coarser mesh size, coarser size of plate element elsewhere at the boundaries, for example. Basically, you want to capture more the effect of the stress concentration. We may need to go for a finer mesh in locations where we are expecting stress concentration. So by using the size control, we can control the distribution of the node points, the nodes, how fine and how coarse, and what areas we need to make fine or coarse, we can control using size control option. So there are different ways of doing size control. So I'll just go through. Say if I want to control the size of these two, size of the mesh at these two edges. Okay, I put in number of divisions I want. Okay, so number of divisions, let's say 5. Okay, just look at preview and it will show you how the nodes will be arranged. Apply. Now let's say for these two edges, I don't want equal size of the mesh everywhere. I want a variation, so I want to have finer mesh near the ends and a coarser mesh in the center. So I can use the grading option. Okay, so grading option, it will come up with arrows like this showing the direction of the local direction of the line. So start length I can put as 0.1 meters and end length put as 0.25. Okay, and symmetric seeding, and number of divisions, let's say 20. Okay, so it looks like this. It starts from 0.1 and at the center linearly varies, becomes 0.25 meter, and at the ends again it becomes 0.1. So symmetric. You can increase the number of divisions and use any kind of rules of meshing that you want to use. So if I make it 0.05, it will become like this. Okay, so 0.05 is the mesh size at the ends. Okay, you can also keep 0.05 constant up to certain length. So for example, I put up to 1 meter. Oops, sorry, it's ratio. So say up to 10% of the beam length. I want to keep constant 0.05 meter as the mesh size. Okay, and then vary it up to 0.25. Okay, so I'll just keep it as 0 and will vary linearly from 0.05 to 0.25 at the center, and click OK. Okay, so we have got the mesh size control, and now if I use the map mesh feature, map mesh. Okay, since this is a wire, so I cannot directly use map mesh face. There is another option called K-edge area. This is used to create a mesh using lines. Okay, so first step should be to create node points on the line. Okay, and then if your area has 4 edges, then you can directly select all the 4 edges using auto feature. And then if I look at the preview, it will show me 20 divisions on the longitudinally and 5 divisions in the transversely. So if I click on apply, you get a mesh like this. Okay, so you end up with less number of elements. Your analysis results will still be accurate because you're taking into account good number of elements and nodes in the regions where there is stress concentration. Okay, and your analysis speed will be faster. So compared to what you got earlier when we had 0.1 meter mesh size, this is a much better, this will give you quicker analysis as well as good results at the same time. Now for irregular geometries or curved geometries, let's see how to use the same feature. So if I go to geometry, curve, and quickly generate few arcs. So if I generate, that's the center point. Right, so that's the one of the arc, and I'll just generate some arbitrary lines. Okay. 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 Now, how do you automatically mesh this? Well, you first have to convert it into face. So I'll just show you how to convert a set of lines into a surface. So first of all, you need to intersect all your lines, so to convert them into edges. So in this case, well, all of them are individual lines, but let's say if you have 2 lines crossing over each other, then you won't be able to convert them into face unless you intersect. So curve and intersect option, you can just select all the lines here and apply. So they will convert into edges, and then you can use the surface, create plane face, select all the lines and preview. See, it's converted into surface. You click OK. Now how do you mesh it? You just go to auto mesh, face, click on the face and just give a mesh size that you want, say 0.1 meter, and click OK. So you get a mesh like this. But this is a very irregular mesh, okay, and also it uses a lot of elements, okay. So if on a bigger model, you may struggle to run the with the runtime, the analysis runtime, because of a lot of elements. So to make the mesh more uniform, we take the help of the map mesh. Okay, so again we go to size control. Okay, and we give the sizes along edge. Okay, so what I'll do is remove the previous edge seeds, so to avoid confusion. Okay, and just put edge seeds here. So I'll just put number of divisions directly. So say say 5 divisions. Select this edge and this one as well. Okay, and apply, and then select this edge. I'll give 5 divisions again, apply. Okay, so this will be my, if I assume it as a quadrilateral, then these two curves will be one side, this will be another side, and then these two will be the rest of the two edges of the quadrilateral. Okay, so I select this and give 10. Okay, apply, and finally this one give 5 again. Now I go to mesh, map mesh, k-edge area, and use manual mapping, because now this number of edges are more than 4. So manual mapping, and I use these two as one side, these two as another, this one as another edge, and this one, then I select this one. Okay, and then click OK. So I've got a more uniform mesh, less number of elements. Okay, and the accuracy will be also good for this type of mesh. Okay, so you can use these tools to control your mesh. Okay, now once you've got a 2D mesh, you can always use it to generate a 3D or a solid mesh. Okay, so let's say if I want to convert this into a solid, I go to mesh, protrude mesh, and a different option I can use, say extrude. Yes, selected all these elements, direction, say Y direction. Okay, and number of times, and the property. So just click here and define a solid property. Okay, I'll just reduce the, see, so it will become a solid geometry, solid mesh. You can do several other things. You can rotate the geometry. For example, if I select this mesh, protrude mesh, and if I use revolve, select this, select an axis for revolution, say vertical axis, and number of times, angle say 5 degrees, and say 20 times. Oops. Okay, and click OK. So we've got this type of geometry. Okay. So this way you can also generate 3D volumes. And also you can take control of the mesh size. So if you see, if I had to model it as a solid, okay, so if I, let's say, going back, if I change my plane to XY, okay, and I just go to geometry, curve, create, say, polyline or arc. Okay, and I go to geometry, curve, line, and I connect this line, and I use make face option. So surface, create plane face, convert it into a face, and then use this geometry to create solid. Okay, so extrude, use this geometry, select extrusion direction is the Z direction, so I click on the Z axis and click OK. So I get a solid directly. Now if I were to mesh this solid, I'll use the auto mesh solid feature, select the solid, maybe define some mesh size and click OK. Okay, so you won't get a very regular mesh if you use directly the auto mesh solid option for this type of geometry. Although there are features for using hexahedral elements which are more uniform. Okay, so those tools can be used, but then you will also end up with more number of elements. Okay, and if you want to go finer, okay, the same size, similar size will be applied to all the geometry. Okay, whereas if you use this type of technique, okay, you can control the mesh size. So based on the complexity of the model, you can choose to go for either directly modeling or automeshing the solid, or you can first model it as a plate with size control, okay, with finer elements and coarser elements properly defined, and then create the solid out of the plate to get a more efficient mesh. Okay, so that's how you generate different types of mesh and manipulate the geometry. So now I'll actually take up an example of steel connection. Okay, and we'll look at buckling analysis and nonlinear analysis on that steel connection. Okay. Okay. I'll pause here and try to answer some of your questions. So there's a question that what is the advantage of making the mesh finer? As I said, for regions of stress concentrations or where you are applying the load, you want to capture the stresses accurately in those regions. So that's why more number of nodes and more number of elements will allow you to give enough stress points so that you can get a good picture of the stress distribution at that location, because stresses are always calculated uh, at integration points or Gauss points for an element. So if you have this one block of element, you will have some number of integration points in it. So stresses will only be calculated there. So the more integration points you have, the better average you can get, better contours you can get for the stresses. Okay. Okay, so now I'll click on new project again. Okay, and now we'll go to modeling of tubular type of connection. Okay, so we have a column which is tubular section, and also bracings which are connected, welded to the column. Okay, so it's completely steel connections. So first I'll start with modeling the geometry. So it's a cylindrical section, so we have got some of the basic shapes available under primitive feature. Using the cylinder option, we can create a cylindrical shape. So let's say radius I put in as 0.5 meters and height as 3 meters, and I'll convert it into solid. Okay, so if I look at the preview, it looks like this, and click OK. So I've got a solid now. Now what I'll do is I will rotate this solid and create few copies to represent the bracing. Okay, so it will be like a K shape. Okay, and we'll also see the different geometry transformation tools. So if I select this element, this geometry, okay, I can right click and go to transform, or I can go to geometry and transform. Okay, same options. So I can right click, transform, and rotate. Revolution axis, okay, you can directly select it. It's this axis here, and then the angles of rotation. So I have the braces at different angles. Okay, so first brace is 60 degrees with respect to the x-axis, and the next brace is 50 degrees with respect to the first brace. So it looks like this. See, before you click apply, we always preview it, so we know that how it looks like. Okay, so 60 degree and 50 degree. Okay, and that's it. Click OK. Now the braces are not the column braces are not exactly the same dimension as the column. Okay, so you might want to scale them down. So what I'll do is select both these entities, right click, transform, and scale. Okay, so scaling option is very useful. You can select the scaling center point. So with respect to this point, scaling will happen. Okay, you can have uniform or non-uniform scaling. Uniform scaling means X, Y, Z, all dimensions are shrunk or magnified. So I'll use a uniform scaling, so 0.75. Okay, and click OK. So they are scaled down, front view. Now you can also make the solids transparent, so it's easy to view what's going on inside. So you can go to the works tree, okay, and right click on the first section. So you can select objects by clicking on the shape itself on the works tree. So right click, transparency, and I'll increase the transparency. Okay, so it shows the connections within. Okay, now I'll move these diagonals by some distance. So use the transform translate option. Select the direction, it's the z-axis. You can also select 2-point vector. If you have 2 points marked somewhere, it may not be XYZ axis, but you can just click on the 2 points to define the direction of copying. So it's Z axis, and I want to move this object. So move distance, and I'll just type in as 1.8. Let's see the preview. So it's moved at that level. Apply. Next, I'll move this one. Again, the same direction. But this one I'll move by 1 meter. So that's how it looks. Okay. Now, the internal part of these solids are not supposed to be there in the reality. So it's going to be welded only on the outside. Okay. So I have to remove that internal, the overlap region. Okay. And basically what it means is I have to cut through this solid. So I've got some openings at the connections. Okay, so those openings I have to create. So for that we have an option called Boolean cut. Okay, so let's see how we can use it. So we have basically 3 Boolean operations: fuse, cut, and common. Fuse means we can convert all these 3 solids as one solid, so they will be fused together. And when we mesh it, it will be all meshed, converted into finite elements as if it was one solid. Okay. Cutting means we cut through an existing solid using a tool object. So let's say if this column is the master solid and tool objects are these 2 places, and when we use a cut option, it will create openings. Okay, and it will remove the volume which is shared by these 2 geometries. Common means it will only take the common volume, overlapping volume, okay, and delete rest of the things. I will be using cut option, master, and Boolean tools. Select these 2 as tools. Okay, if I look at the preview, you see it shows like this. It's cut through. Okay. Now I don't want to delete the tool objects, so I've removed the delete tool objects option and I clicked apply. Okay. So you will immediately see that there are few markings at the connection level. Okay. So the opening has already been created. Next thing is we also need an imprint of the master solid on the tools. Okay, so we use this one as the master now and this as the tool, and apply, and then this one as the master and this as the tool, and okay. Right, so if I now look at, if I display this show only, we've got this shape. Okay, if I say show only, so I've got the imprint here. Okay, why I needed this imprint? Because I'll be deleting this portion, the left hand portion from the diagonal, because there is no diagonal member going inside the column. It's all welded on the outside. Okay, now the thing is that it's a tubular section, so I've modeled it as a solid. So what I'll do is remove the solid, convert it into a hollow section. Okay, so in order to do that, we have a feature called explode. Okay, explode can be used to break down any shape into a sub-level shape. So a solid into face or edges, a face into edges, an edge into points. Okay, so if I select all these solids, okay, and select face, okay, delete the original solids, okay, and click OK. So these are now converted into individual faces. Okay, you see I can select individual faces now. Okay. So next step is to delete whatever face I don't want to use. So I don't want to use this one. So I press delete. Just click on that. Don't want to use that one, delete. Okay. And using the select by polyline, I can create an intersection point like this to highlight all objects. Okay. And then press delete. Okay. Delete. Okay, then select single. Delete. And we don't want this one either. Okay. So we've got a tubular connection. Okay. Now we just mesh it. So we go to mesh, auto mesh, face, properties. So we have to define some thickness. Okay. So these two, diagonals and the columns can have different thicknesses, different materials. So let us define that. Material, let's go to material. Okay, so these are shortcuts for materials and properties. Okay, when you mesh it, you will have a shortcut icon here, or you can also go to analysis, material, define materials. So it will be steel. Okay, so ENS says column is made of S355 grade. Okay, and it's we'll use non-linear properties. So for steel, we use von Mises. Okay, which is an elastoplastic material behavior. We can also define hardening or softening function for strain hardening. So after the first yield, we can define the behavior of the stress strain curve. But in this case, we'll just stick to elastoplastic behavior. Okay, and just put in the maximum yield stress. So that's 355. Okay, apply, and then select second material as 275. 275. Okay, and click OK. So that's it. Two nonlinear materials defined, and we'll define two thicknesses too. So property, 2D property, and thickness for like column is say 0.05, 50 millimeters. Okay, apply, and thickness for the brace say 40 millimeters, and material is 275. Click OK. Now we can mesh them. So auto mesh, face. First we'll mesh the column. So let me select all the, so using the line, again polyline option, we can select all the column faces, so 4 faces at one go. Define a mesh size. Okay, so we can go for say 0.1. This is column, and apply. Okay, so we get the mesh generated. For the braces, we just select all the braces together, 8 faces selected. Change it to brace. You can give a different name here, brace, and click OK. Okay, so that's how generated. Okay. Now for supports, for applying boundary conditions on this, we use analysis, boundary condition option, constraint. Okay. Now you can apply boundary conditions on nodes or on the geometry. The same goes for loads too. Boundary conditions and loads can be applied directly on the geometry, which means that if you delete the mesh, you still have the boundaries and loads intact. Because sometimes we do need to revise the mesh. Okay, we may be getting some results, and we want to check if the results vary too much if we change the mesh size. So we may refine it, delete the existing mesh, mesh it again, and see what the results are. So while doing that, we don't want boundaries and loads to be deleted. So that's why you can apply boundaries and loads directly to geometry. Okay. So you have options for applying it to nodes. So for nodes, you just select all the base nodes. Okay, and you can apply full fixity, pinned, or free, or no rotation. Okay, so you can basically check which degree of freedom you want to restrain. T1, 1 to 3 are X, Y, and Z globally. Okay. So if I select nodes, okay, and preview, so that's all how the supports will be applied. Okay, if I do it by curve, okay, I can select the curves like this. Basically 4 curves, and still they are shown like this. Okay, so you applying it on curves means if I delete the mesh, boundaries will still remain. So apply, then I go to loads. Okay, now what happens is when we do this type of analysis, we normally have the loads as point loads, which we calculate from a simple frame analysis. Okay, so from a simple frame analysis, we may get some axial forces in the bracings and in the columns, some bending moments. So some forces we get, but these are just point concentrated forces, okay, acting along the centroid. Because when for simple analysis, we model this geometry as just lines. Okay, so just 3 lines. Okay, and we calculate the force along that line, centroid of the line. So those forces we will get from simple analysis and calculations, and we want to apply those forces here. Okay, but since they are point loads and we don't have a single point of application, okay, so we need to create a point at the center, okay, which will represent a centroid, okay, and connect that point to the periphery, to all these nodes, using what we call rigid links. So let's see how to generate such type of rigid links. Okay, so so we go to properties, others, and create rigid link. Okay, and call it rigid link, rigid body. Okay, and we click OK. So rigid property for the rigid link has been generated. Then we go to mesh, node, create. So we are creating a node at the center of this tube. So there are different ways of creating node. You can directly enter the coordinate if you know the coordinate of this point, or you can use some other techniques like between 2 nodes. Okay, so we'll use this technique. We say create a node between this node and that node, so 2 diametrically opposite points. Okay, and click apply. So node is generated, and similarly we can create a node here, this node and that node. Okay. Now this node has been generated, so we can connect this master node, the central node, to all other nodes using rigid link. Okay, so we use the option mesh element, create link, use rigid link, select master node, and using the polygon selection, you can select all the other nodes like this. Okay, and you click OK. So what happens is a rigid link is generated, so the point load will be distributed uniformly to all these nodes. Okay, so I'll not do on the other side. We'll just apply a load here. Okay, So loads, okay, force, point force. So based on the type of the load, you have either point force or pressure. So we'll be applying a point load, so point force. Okay, so again I'll name it as axial force. Okay, now you can apply force in different direction. So if you are applying an axial force, you know the components in x and y, x and z. Okay, so you apply in F1 and F3. F3 is z, F1 is x. So horizontal is x, z is vertical. So you apply the two forces, and that will be converted into, say, 150, something like that. You select this node. Okay, maybe give a different direction, and it shows like this. Okay, so preview looks like this. Okay, so this needs to be calculated. What is the correct based on the correct angle? Okay, there is also an option to directly assign it in the actual direction. Okay, that comes under the direction direction option. Okay, so you select the direction, right? So what you do is first of all you need the vector. Okay, so you go to geometry, measure distance, use snap. So this option, geometry measure distance, can be used to measure distance between any points, any two nodes or any 2 points. Okay, so what I do is I use the snap node option and snap between this node and this node. So it comes up with a direction with a vector with the distance, which will act as a vector. So I just copy it and I paste it in this text box. Give this a name, select the node, which is this node, and put the value, say minus 100 kilonewton. And now if I see, sorry, it's plus 100, it's compression. So now if I see, it's right in the correct direction. Okay, so this can be used. So that's how loads can be applied. Okay, and then after you've done that, we set up the analysis settings. We go to analysis case. Okay, we add linear static analysis. You can define linear static. Okay, which type of loads you want in the analysis, you can select from here and drag and drop in the activated column. Okay, if you don't define any elements in the activated column, all the elements will be used. Or you can selectively choose if you want to analyze only the bracing, or only the column. So you can drag and drop those elements in the activated column. Same thing goes for supports. If you have multiple types of supports, you want to use only certain kinds of supports in the analysis, you can drag and drop those supports here. Or otherwise, if you leave it as it is, everything will be used. Apply, then buckling. Okay, so linear buckling, again which load you're going to use, and in the analysis control we select number of modes of buckling, so 10 modes, and positive critical load factor or eigenvalue, and apply. And few other things, non-linear analysis if you want to do, because we use a non-linear element, non-linear material, so we may want to look at the material yielding. Okay, when the steel yields, so non-linear static, again which load you want to use. And then output control, we can select the crack strains or plastic strains. So if it's concrete, then crack strains, or steel if it's plastic strains. So it will tell us which region, which steel elements or nodes have gone into plastic zone. Okay, or which portion of the solid has yielded. Analysis control, since it's a nonlinear analysis, we do it in steps. Okay, So here are a few things which you need to be need to know about. There are different analysis algorithms for nonlinear analysis, different ways of solving a nonlinear analysis. Initial stiffness, Newton-Raphson. These are the basic two methods. Okay. So initial stiffness is basically when I say number of load steps, when I break the 100 kilonewton load into 10 steps, and I'm going to apply it in 10 small steps. Okay. Initial stiffness means the stiffness of the first step. Okay, the initial stiffness to start with will be used for all the steps. Okay, so this won't account for the change in the stiffness as the load steps increase. Okay, so it's not a very accurate method. Okay, Newton-Raphson is the most widely used method for all the nonlinear analysis. It covers the change in stiffness. Okay, and considers the displacements from the previous steps. Okay, so this is the method that you should be using for all your analysis. Sometimes we may need arc length. This is for situation. This is a special feature within Newton-Raphson. So this is nothing different from Newton-Raphson, except that in arc length we can take care of situations like snapback. Okay, if the stress strain curve snaps back. Okay, and for those type of situations, arc length iteration can be used. Okay, but Newton-Raphson is the most commonly used nonlinear iteration scheme. Okay, then we put in the number of steps we want, so 10 steps, and the convergence criteria. This is also very important. All finite element software have displacement as the primary variable for solving any equation internally. So displacement norm should be the convergence criteria, and according to most conventional finite element software packages, 0.001 is a default convergence criteria that we should select. Okay. For certain cases, if your analysis goes into the post-yield region, is mostly in the post-yield region, then you may want to use force norm 2 in conjunction with displacement norm. Okay. What it means is that what these norms means is the software checks for between each step of iteration. It checks the error based on displacement or based on force or based on energy. Okay. So if that error is within this tolerance or less than this tolerance value, then it will stop at that stage and go into the next step of iteration. Otherwise, it will keep on iterating up to the number of steps you specify. Okay, until it diverges. Okay. So that's the convergence criteria. We normally use displacement norm. Okay, and that's it. So click OK. Now just go back to results now. So when to run the analysis, we go to analysis solve, and it will come up with a table. You can check which analysis case you want to run. Okay, and you can run only all of them or few of them here. I'll open up the model which is already analyzed. Okay, this model is already analyzed, and we're looking at different results. So linear static. Okay, displacements, you can see dx, dy, dz. Okay, the legend will show you the values based on different colors here. So maximum displacement is 0.003 meters. If I change it to millimeters and newtons, so 3 millimeters. The properties window will allow you to modify the legend. So if you're in the legend, you want to change your legend into an exponential format. So you click true here and apply. You get exponential display, or display in exponential format. Stresses. Let's look at the stresses. Von Mises stress. Okay, 115. And top of steel and bottom of steel. So basically, the shell will have two surfaces, top and bottom. So it shows the stress levels in the top and bottom. Then buckling. So if I look at buckling, since you can also browse through different cases from the top here. So linear buckling, different modes of vibration, modes of buckling. So mode 1, and if I apply displacement, so that's the vibration, buckling in for mode 1. Okay, buckling mode shape. You can turn on both deformed plus undeformed to compare how it is buckling. So it's basically a lateral, the transverse direction. Okay, post style will allow you to add few more things to your results. So you can look at the mesh. You can also create an animation. So if you click on the animate button, you can animate how it's going to buckle. Okay, probably increase the scale of the deformation from the properties, so 5 times. Okay, then some other mode of buckling, mode number 2. Okay, mode number 3. So it's twisting. Okay, so that's how you check the different buckling mode shapes. You can save this animation as an AVI file. Then nonlinear analysis. So go to nonlinear displacement. Okay, so that's the displacement. Okay, and if I go through different steps, you can see 1.5 millimeters, 3 millimeters, 6, and the load factor is shown here. Okay, so it doesn't mean that nonlinear analysis will always have equal load factor. You can always change the load factors, load steps. So in the nonlinear analysis control, you've got either you can select 10 automatic steps, or you can use user defined step and put in your own load factor. Okay, say if it's not diverging, not failing even at full load, then you can keep on increasing the loads, adding different factors, and see what the result is for higher loads. Okay. Okay, 10. So you can say that at when load factor is 10, then this starts yielding. There's a failure here, abnormal deformation. Okay. Now this is a key thing, because if you see the buckling mode shape, first mode, the critical factor is 90. So 90 times the load you apply, still it will not buckle. 93 is the load factor. So even then it will not buckle, but it doesn't mean that it will not fail, because it can fail by material yielding, and that can be checked from a material nonlinear analysis, which is a nonlinear analysis which we saw here. So typically it fails somewhere. If I look at the deformed shape at load factor 10, so it fails at load factor 10 due to material yielding. How do we know it fails? The normal deformation, we can also look at the stresses, how the stresses vary. So von Mises stress, let's say if I look at stresses for different steps, see maximum stress allowed was 355. Okay, so you see, so here at some of the regions, You have got very high stresses. So that means it's yielded. You can also check the status of the element, plasticity status. We click on bottom plasticity, you see the blue zones represents the, see PL is written, represents the plastic, the elements which have reached plastic region. So it's completely failed. If I go to previous step, you see, you will find that this particular connection kind of yields. Okay. And if I look at the load factor 4, you see there fails over here, here. So that's how using the nonlinear analysis you can check which connection will fail first. Okay, so it's very useful for this type of analysis, connection analysis. Few other results that are useful. If I go back to results, let's say linear static, displacement or stresses we are looking at, let's say. Okay, undeformed. Now if you can see the values here on the legend, you can make out what's the maximum stress, but you want to know the stress values at each and every node, then there is an option called probe result. You can click on any node to see the value of the stress. Okay, it will give you the values here. You can also extract the results in on a line. So if I say on curve diagrams, okay, draw a line from, so I want to look at all the stress variation from the top to bottom. Okay, draw a line from top to bottom, give it a name, and define the direction of plotting, say -5 direction, add, and diagram. So what we show is a diagram plotted in the y direction, showing the variation of stresses on a given line. Okay. All right. Then you can also plot the table of results. So if I select extract result and say I want the results of say 1 means stress, I want for certain elements, certain nodes elements here. So selected them, they are listed over here, and I go to table, and that will show me the stress of each element in a table format, which I can copy into Excel. Few things here regarding the results. Reactions and displacements are always displayed in the global axis, so X, Y, and Z are the global axis. Then stresses, SXX, YY, ZZ, these are all global axis. SXX means stress in the global X, global Y, global Z. Okay, then same thing goes for your strains, strain values, strains in X, Y, and Z. And then plate forces, these are local plate forces. Okay, so local axis of each element. Okay. Now LO plate means lower order plate element, which means if it's a quadrilateral plate, then it has 4 nodes. If it's HO plate, which will be higher order plate, which means quadratic, means it will have mid-side nodes too. So it will be 8 noded plate element. Okay. Right. So let's now look at the other example for reinforced concrete analysis. Reinforced concrete analysis, we will be doing reinforced concrete analysis for a rectangular beam, simply supported. We'll be applying loads, and we'll be doing a nonlinear analysis and looking at how the crack propagation occurs. we'll be adding reinforcement and then um, see some of the results. Okay. There is another question about the concrete beams. What is difference between the modeling technique of faces and solids in concrete beams? It's nothing but if you want to do a 2D analysis of a beam, we use faces. Okay, we model the beams as 2D face, and we apply all the loads in one plane. Okay, loads in one plane and all the boundaries in one plane, and we do a 2D analysis. This will give us the results in the say XZ plane. But if we want to look at the overall effect, that is the rebars in transverse direction, placement of the rebars. If you want to capture the whole 3D effect, okay, add shear links in the beams and all those things, then we need to go for solid modeling. Yes, that is the only difference. One is 3D approach and 2D approach. Both are fine. It's depending on how detail you want to go for the analysis. Both have their own pros and cons. If you model anything as plate elements, you will be able to extract forces, local forces directly. As we saw just a few minutes ago, for steel, we were able to get local forces. Okay, and for solids, we only get stresses. So you will have to use different techniques to calculate the forces, bending moments, and etc. from the solid geometry. So this beam I'll be doing as a solid. Okay, we have a tutorial for 2D concrete beam analysis which you can follow it's on the website on the tutorial section. It's a shear crack propagation analysis. Now for the rectangular beam, I'll use geometry primitive feature, draw a box section. So box simple like this. Length, I'll give it as 3 meters. Okay, and width keep as 0.5 and 0.5. Okay, let me just take it as 10 meters, and one it will be easy to calculate the rebar spacings and everything. Okay, so 1 meter by 1 meter and length is 10 meters. Okay. All right. Now what I'll do is so I've got this solid beam here, and I'll make it transparent. So when I model the rebars, I can see where I'm placing the rebars. Okay. Now for modeling the rebars, I will use the work plane again, XZ plane. Look at it from the normal view. Okay, and I'll reduce the grid spacing. So grid setting I'll make as 0.1 meters and click OK. So I've got this type of grid system now. So and in 1 meter by 1 meter section, so the clear cover I'll keep as effective cover I'll keep as 100 millimeters. So geometry, curve, create on work plane, and line. Okay, so I draw the line, use the grid snap option, and just draw a simple line from here to here. Okay, and another line on the top from here to here. So top and bottom rebars basically. To make it more accurate, I can also add links here, but I don't want to go into modeling of links. Okay, that's the procedure is exactly simple. How we draw the main rebars, we draw the links that way. Okay. Then I'll remove the grid. Okay, and look at it from side view. Okay, now what I'll do is I'll move these rebars slightly inwards. Okay, so they are right now at the face of exactly on the face of the beam. So I use transform, translate, move, and in the y direction 0.1 meters. Let's see um, the preview. Okay, they moved inwards. You click apply. Now select them again and we'll create few copies. This direction is again y direction, uniform copy. Let's say spacing is 150 millimeters and number of times, say 5 times. Let's see how it looks from the top. Yep. Okay. So we have copied all the main rebars. Now I'll apply some material properties. Analysis material. Create. Okay, so concrete, let's say strength is C40. And we'll look at cracked analysis. So we use the material model called total strain crack. So total strain crack material model will be used. We have a full manual which describes all these parameters, so I'll not go into the details here. Basically, the way the crack propagates can be controlled by these parameters: fixed or rotating, stiffness, type of stiffness, or confinement effects. What is important is to define the functions properly, the behavior of concrete properly. So tension, compression, and shear behavior of concrete has to be defined properly. So if I select tension function here, the model type is tension. Function type, so definitely not elastic, otherwise it will not fail at all if there are tensile stresses. Okay, you can select linear, multilinear. Multilinear is useful if you are doing an experimental data if you want to include. So stress strain behavior of concrete in tension, you can copy paste from Excel. Exponential, DF is the fracture energy. Then an Hodic model, constant elastoplastic type of behavior. We'll use a brittle behavior which is recommended by most design codes. So it's brittle behavior, and let's say allowable tensile stress is 3 megapascal, so 3000. I put the name as tension and apply. Then I'll define a compression function. Compression function again can be multilinear based on experimental data, parabolic, linear hardening, saturation like this, constant, or Thorenfeld. So I'll use the Thorenfeld equation. Put maximum characteristic strength as 40 megapascal as compression. And then shear. So shear I'll assume as elastic. You can also go for a constant shear reduction, some value of reduction of shear modulus. Okay, so I'll just select elastic behavior here for the shear and define a different name. Okay, so I'll just make sure I select the correct function in the right category. Okay, and then apply, and then I'll define another function for the rebars. Okay, let's say ENS and S460. Now for rebars, steel we use von Mises, so we can put in the maximum yield strength of rebar. Okay. Okay, so basically when we define a nonlinear material for steel and concrete, we can, from the analysis, we can figure out what is the mode of failure. Is it due to yielding of rebars, or is it due to crushing of the concrete, or shear failure? Because we have defined all these functions discretely, when we do the analysis, by looking at the crack propagation, by looking at the rebar stresses, we can make out that what is the failure mode. Okay, next is assigning properties. So property, create. Now it's a solid model, so 3D concrete, and material is concrete, and click OK. For reinforcement, we have a special property called reinforcement property. This is used for both reinforcement and tendons. Okay, we select reinforcement. Okay, it's called also known as embedded truss in some other software packages, so you can relate to that. Embedded truss or embedded bar element. The benefit of using bar element is that you don't need to worry about the connectivity of the rebar with the surrounding solid. It's all taken care of by the software automatically. So name, I'll give it as rebar. Material is the S460, and cross-sectional area is the area of the bar. So I'll select a 25 millimeter bar. If it is a tendon, then we need to define the loss parameters, relaxation losses, and the friction loss and anchorage loss. Okay, and it will be modeled as a tendon where we can apply pre-stress forces. And here we just go for reinforcement and apply, and then bar section, and we click OK and close this. Okay, then next step is to mesh the solids. So mesh, auto mesh, solid. Okay, select it. Okay, we can give some mesh size, 0.1 meters. Apply. Okay, now it's converted into tetrahedral solids. So to make sure it's map mesh, that is regular quadrilateral solids, we can go for advanced option and say try map mesh, or we can directly go to mesh, map mesh. That's also fine. Generate mid-side nodes, again higher order solid elements. For reinforcement analysis, it's better to go for higher order elements because the stress distribution is well captured in this case. So click OK, select it. You can name it as concrete. Okay. Okay, so it's much uniform, more uniform mesh size now. Then for meshing the reinforcement, hide all the solids and mesh auto mesh edges. So reinforcement are modeled as edges. Select all the reinforcements. Property is the rebar. Reinforcement is a bar in solid. So if you're using a 2D modeling of concrete beam, then you will use bar in plate. So you model this concrete as plate elements, auto mesh face option, and you will then to mesh the reinforcement, you'll use bar in plate. So this will become rebar. Click OK. So all the rebars are also meshed. Okay, so display everything. Now I'll quickly define the boundary conditions and we'll look at the results. So boundary conditions, constraint. Okay, so supports, give a name. Now we have pinned conditions over here. So I select few elements from here and apply pinned and apply, and select few nodes from here and make it roller kind of support. So I remove T1, which is X direction translation, and I fix T2 and T3, Y and Z. Click OK. And then loads I'll be applying. So I'll be applying pressure loads on 3D element face. So 3D element face. Name it pressure. Okay. They will be applied at 2 locations. Okay, so let me just so I'll select the faces from here. top face like this and like this. So we'll be applying pressure loads here, and I can add another point, another load point, something like this, and put some value 100 kilonewton per meter square. Preview. Let me show you this way. The pressure is applied like this at 3 different points. And click OK. And then we do analysis, and analysis case, add, and nonlinear analysis. For looking at the cracks, we need to have nonlinear analysis. Output, crack stresses and strains, and analysis control, how many steps you want to apply the loading in. So 10 steps. Material and geometry. So material nonlinear takes care of your cracking behavior. Geometry nonlinear is the large displacement effects. So again, displacement norm, and click OK. And the load that we are going to use, pressure load. Okay. Right, and then we run the analysis like last time. So go to analysis and run, or go to analysis solve to run the analysis. Now this is already analyzed, so I'll open up the analyze model. Okay, so I've taken a different length previously, so it's a shorter beam. Okay, so what we'll look at is the is how the crack propagates and the reinforcement stresses. Okay, so 1D reinforcement stresses. Let's look at deformations first. Let's see how it deforms. So deformation is very exaggerated. We can reduce the load scale factor of deformations, because that's how it deforms. You can also put some plate. You can model up some plate elements or some solid elements, some wood block below this support points, and then apply the boundaries on at the bottom of the wooden blocks to make it more make the stress distribution more realistic. Okay, then so that's deformation. If I keep on increasing, okay, and almost at load factor 50% of the load, you have a failure. Okay, to see how the crack propagates, we can check 3D element status and crack status. So there is initially no crack. So as we go to, we start having cracks here. So load is applied at these 2 locations. You can see how you have these are basically you have some flexure cracks straight away, and then shear cracks you have diagonally, they are reaching towards the support. Okay. Fourth, you have almost all of the beam is cracked, and step number 5, you have full failure. Okay. Now when you model it as 3D, you will be able to see crack propagation in the lateral direction as well. So you will be able to see the effect of having shear links and the transverse spacing of rebars. Now let's look at rebar stresses. Newton millimeters. Okay. So you will see rebar stresses at the bottom, in the bottom rebars will keep on increasing, because as the cracks start appearing here, rebar stresses are increasing, and they're almost reaching the yield limit, which is 460. Okay, so some rebars have already yielded. Okay. And here you have abnormal results because this is complete failure. Okay, now results may not be accurate if your convergence was not good. So when in the message window, you will be able to see, when you run the analysis, you will be able to see what's the convergence or displacement norm. So you remember we kept a displacement norm of 0.001. So all the errors should be within that tolerance, 0.001. And if we see in the analysis, if even after 30 iterations it's not coming less than that, we can terminate the analysis, or we can just click on this option, terminate the analysis in case of divergence. Okay, so it will stop automatically when this condition is not satisfied. Okay, so that's how we can look at the stresses and the crack pattern. Another important result is the forces that we get from the rectangular section. Okay, because it's a solid section, we can't extract the forces automatically. So in order to be able to do that, we have a feature called local direction force sum. Okay, so I'll just display the solids again, undeformed shape. Okay, all right, and we go to post local direction force sum, and we'll add, it's a solid element, so even for plate element you can do the same thing, solid element. So just select the node points, and make it a little clear. Okay, just make it 2100 to okay, and plot. So you see it converts that plane that you select, 3 points on the plane, into an equivalent section with the neutral axis, and the 6 forces are shown here. So you can make several such cuts and save it, and then plot the table, or display the table. It will show you the centroid location for those sections, and the force values. Okay, it's a nonlinear analysis, so you can also look at the nonlinear load displacement graph. Okay, so if I display the result, say if at the center you have got maximum deformation, how to see? You go to values and min, max, and apply. So you have maximum deformation over here. So I can go to post probe result and extract the node number, so 3081, and then go to post and nonlinear static analysis, nonlinear static result graphs. Okay, and add and select this node number. We want the result in DZ direction, and then plot the load displacement graph. So you'll get this type of graph. So you see up to load step 3 you have linear variation, and then suddenly load step 4 you have a variation and a sudden change in stiffness, and then you have abnormal results. So this value is you can ignore. What we can do is to get this graph a more curvilinear type of profile, we can divide the load steps further. So you can use user defined load steps between 0.3 to 0.4. You can break down the steps and or increase the number of load steps, that's also fine, to get more points in the post yield location to get a better graph. Okay, so that's basically from reinforced concrete analysis. Now for some kinds of material, we may not have this kind of homogeneous distribution. We may be having discrete elements, discrete type of connections. So for example, masonry is not a homogeneous material. We define bricks and the joints separately. So for doing such kind of modeling, we use interface elements. Okay, so I'll just quickly show you how to define interface behavior. Okay, so basically I'll again go for solid primitive box. Let's model quickly a box. Okay, and mesh it, map mesh solid with 0.1 meter. I'll just put some property here, maybe 0.25, just to reduce the mesh size. Okay, and then I'll just copy the mesh. So mesh, transform, translate. From copy, select direction is X direction. Four times apply. Okay, now this option is important, merge nodes. Okay, when I copy, these are all copied as separate mesh, but if I use the merge nodes option, the nodes at the boundaries are all merged, so they are connected. Okay, and it's also useful when we generate the interface. This option will be handy because interface can be very easily generated from merged nodes. Select this mesh and translate it vertically. Okay. Okay. So that's the arrangement, and now I'll create an interface element. So for that, we first define an interface material, create interface. So there are different types of interfaces that exist. The most common ones that I used are bond slip to check the interface slip between rebar and concrete. Okay. For all interfaces, we need to define two things. We need a normal stiffness and a shear stiffness. Okay. So shear stiffness will define the amount of the slip occurring, and normal stiffness will define the contact force. Okay. So based on the friction coefficient, and based on the friction coefficient and the normal stiffness, it will determine the friction force that is being applied between steel and concrete, or steel and steel, whatever it is. Coulomb friction is used for situations, for most type of interface condition. This is a basic interface material that is used, very commonly used for checking slip between a steel beam which is filled in a steel infill type of beam which is surrounded by a concrete pour. Also for interface behavior between shear studs in composite section and the surrounding concrete slab. Okay. Again, normal stiffness, shear stiffness you put in, and internal friction angle. This determines the the friction force. Okay, and tension cutoff. So you can, if there is any separation between the two solids that you're trying to interface in between. So if there is any separation, if there is any tension between those two solids, you will lose the contact basically. So there is a cutoff force that you can put in. If you don't put in a cutoff force, that means if there is any tension force, tension between the two solids, you lose the contact and there will be basically no slip, no contact and no shear force, shear interaction between the two surfaces. So that's how the interface works. Combined cracking shearing is a more advanced type of interface. This is used for masonry material where we control both tension and compression. So you can put a cap on the compressive stress as well, maximum compressive stress, and also shear, and you can also put in tension cutoff, maximum tensile strength allowed in that interface. So these are given in more detail in various technical papers for masonry modeling. Okay, so I'll just choose a simple Coulomb friction interface to show you how to generate the interface. So just define a material, define a very high normal stiffness and a very high shear stiffness. Okay, because there should not be any relative deformation normally between the nodes of the two objects that we are trying to interface with. Cohesion depends. If your two objects are cohesive, then you can put the cohesion force, cohesion stress. Okay, and that's it. Just give a name to it, interface. Okay, and then go to mesh, element, create interface element, and we'll define a property for the interface. Select interface from here. It's okay. Okay, so since we have all solids here, so the interface will definitely between two solids will be a plane. Okay, similarly, interface between two plates will be a line. If it's two plates, two faces, my interface between them will be the common boundary, common line. And if it's two lines, then interface will be a point. Interface between the two lines will be a point. So that's how it works. So we'll use plane type for solid geometries. Okay, and select the element. So I'll select the mesh sets like this. Okay, basically I'm trying to avoid any common faces. So using element boundary means using a mesh and selected number of elements, it will generate an interface on the boundaries shared by different mesh sets. Okay, so it will, for this mesh, if you see, it will create an interface here and horizontally here. If I click on apply and go to mesh set, say interface show only, so it's created an interface elements here. Okay, so the nodes should be merged in order to create the interface. Okay, other techniques of modeling interface, if the nodes are not merged, so if I delete this now, deleting this means we have nodes that are not merged, because when we create interface, the software always separates the two nodes out and creates an interface in between, connecting the two nodes of the mesh. So how to check if the nodes are merged or not? You go to mesh node, merge, select everything and click find. It will give you all the locations where nodes are not merged, just overlapping each other. Okay, so if you want to use the previous method of generating interface from the element boundary, you need to merge them by clicking OK, or you can use the interface from the free face option. So create interface element instead of this you use from free face, and you select the face that is free, so it select all these faces basically. Okay, so if I select these two and click OK, and now if I look at interface, I've got interface generated like this. Okay. Now when we are doing interface modeling or discrete modeling, we generally model the solids. Say if it's a masonry, we generally model the bricks as elastic material, and the interface as is always a nonlinear material. So interface is treated as nonlinear material and the solids are treated as elastic material. That's how we normally do it. So if I go to open the model which I've already analyzed. Okay, so in this model I basically applied loads in stages. Okay, so I'll just briefly go through how to build construction stage. So construction stage, you just define a construction stage. Okay, now this is construction stage. Define a construction stage, you define which elements you want to use in the construction, so drag and drop selected entities here. Then boundaries, so I'm going to fix the base in the first stage, fixed in the first stage, and then loads that I'm going to apply. So in the first stage I'm going to apply vertical loads. Okay, so just to show you how the loads are applied, so applied vertical loads throughout on the top. Okay, and also applied fixed boundary condition at the bottom, fixed boundary condition at the bottom. Okay, and in the next stage I go to construction stage, so I click save to save the stage. Then this next stage is the stage where I apply the next stage is the stage where I apply the horizontal force, so just the horizontal force and some horizontal boundary conditions here. Okay, so force I've applied from the left hand side, and this force I'm going to apply in steps. Okay, so 10 steps. Okay, and all of these are having interface between them. Okay, all of them have interface elements here. Okay, so now if I run the analysis and look at the results. Okay, so stage 1, and just remove the result values from here. So you'll see that there is a connection loss at the interface over here because the load is applied from the top. And as I go to the next stage, stage 2, and so on, I keep increasing the stresses and stages, and load is applied from the top left, and you will see separation if I go to some other stage. See, there is the separation is generated because there is tension in between the two solids, so there is contact separation. You can also measure the interface forces. So what shear contact forces, nx is the contact force, so whichever is red means contact is lost there, and because some contact at the bottom. Okay, so solids have lost contact basically. Okay, and when every interface loses contact, you have a failure. Okay, So that's how the interface works, and you can model interfaces between different solids. So that brings us to the end of the MIDAS FEA features. So if you have any questions, you can type them in the questions window. We'll try to answer some of them. There's a question that why I defined the tension in concrete as brittle, not the Hordic model. That's because I said that most codes use brittle behavior of concrete for tension. For more realistic concrete behavior, you can use experimental data. You can use the other models available. Okay, so that brings us to the end of the presentation. If you have any questions, you can always email us at uksupport@midasuser.com. Okay, so I'll just send the our our contact address to all of you. Okay. All right. So thank you for attending. We have recorded this session and we'll be sending out the links once we upload it. Okay.